Good evening, my dear JEE 2026 warriors, all my droppers and my freshers class 12 students. Welcome aboard to day 1, lecture 1, chapter 1 of your 12th standard physics. And we are starting with electrostatics, Gauss law, potential, all those concepts. So, in this particular lecture, you are going to learn everything about electrostatic charges, their properties, methods of charging, Coulomb's force, and superposition principle. So that's the agenda of today's lecture. And in this lecture series, we are doing the lectures, such that the chapter is completed in multiple lectures, and in every lecture we do some subtopics of that particular chapter rather than doing a big marathon where after 3 4 hours students are disinterested, you lose focus, or the teacher only starts speeding up things because obviously it's a long journey. So we don't want that. We want every single concept to be taught in detail. That's why we have split the chapters into lecture 1, lecture 2, just like how it happens in your coaching, whether it is offline or online. That's what we do. And that's the best way. It brings in that sincerity, regularity, and consistency. So, welcome aboard. Hi, Aruneshwar, Vasuki, Nitika, Aishwarya. Welcome, Ibu. Welcome, Namneet. Hi, Siddharth. Yes, nice to see all of you on Vedantu JEE English. And I'm so glad you guys are here. And quickly smash this particular like button down there. And let's see how many of your droppers are freshers. We have a lot of fresher students. Wow, that's cool. So next year you are getting through JEE 2026 with an amazing, amazing result. Keep it up, guys. And let me also remind you that if you are exploring any of our offline centers, the link is there in the description box. You can book a site visit right away, right now. All right. So my quick intro would be, yes, this is your captain, Shreyas. You can call me Capto Captain. And I have been teaching, guiding, mentoring, nurturing kids for more than 13 years after working for almost 3 years in an engineering software company. And I love teaching, I love physics, and probably that's one of the reasons for why I would have scored really amazing marks when I wrote my JEE advanced exam almost 20 years back. And here I am. It feels very different when I wrote the exam versus when you are writing the exam. A lot of competition, lot of resources, lot of differences, but the enthusiasm, the target remains the same, and that is IIT. So I did my graduation from NIT Nagpur and then research from IIT Bombay. Hopefully you too are going to be one of the leading educational institutes. You are going to be in one of the best premier league colleges very, very soon. Okay, so subscribe to the #1 J English channel, which is Vedantu J English, and also mark your attendance. That's very, very important. Okay, and a big congratulations to Daksh and all the students like Ketan and Prakhar who secured really amazing rank this time in JEE Advance. And the best part was, even in Karnataka, we have so many toppers. I mean, state-wise, we can go today. I'm showing you Karnataka results. By the way, Daksh got 120 out of 120 in maths. We had Prakhar, Anubhav, Ketan, Sabyasachi, Tanav, Manish, Vipul, Sahil, Aryan. All of these amazing students, guys. And almost the ratio is 1:3. So out of every 3 students in Vedantu, one is clearing JEE Advance. That's like 33% selection ratio. So if you want to visit any of our offline centers, feel free to do so. All right. And we have the new center in JP Nagar, Bengaluru. And of course, a lot of scholarships are being offered based on the entrance test, which is called IVSAT. All right. So let's begin. Yeah. Uh, yes, I do teach in the Vedantu batches. The Sigma J batch 2026 is our batch. So the Sigma batch, which is there, you can see the link over here. This is the batch where I am teaching along with PNJ sir. So we all are a part of the Sigma 2026 batch. Yes, definitely. You will also find my VBuddy recordings. Sir, may I know your age? Ayo, you make a guess, man. Now I've given you enough information for guessing my age, right? Okay, so let's begin. So let's talk about electric charges. Long time back, Benjamin Franklin believed there are, these properties associated, like a fluidic property associated with matter, which cause this mysterious force of interaction when you rub things with each other, like you might have done with a comb. You might have done this with a plastic comb. I have a hairbrush, it won't work with this. So you comb your hair and then you take that comb and it will start lifting bits and pieces of paper, right? So that force is not gravitational in nature, it is electric in nature. So when you rub things, there is some mysterious thing which gets transferred from one body to another body. That thing is called as an electric charge. And he found that two identical such properties always repel each other, and two opposites of such quantities end up attracting each other. So similar things of such a quantity which gets transferred repel each other, and the opposite of those mysterious quantities which produce that forces, they attract. Opposites were attracting each other. So they had to name it something. So arbitrarily you can call one as positive, automatically the other will be the opposite sign, that is the negative charge. So electric charge is is an intrinsic is an intrinsic intrinsic scalar property scalar property of matter. Scalar property of matter. Intrinsic means it is a part of it, it is an internal part of it. Just like if you ask me what is Shreyas sir's intrinsic property, like his weight, his age, his height, these are all internal properties. Okay, all right. So these are there just because Shreyas sir is there, that's all. Right. Now, the charges are of three types, three categories. The first one is a negative charge, which is the best example for that is an electron. Electron possesses a negative charge. The next one is a positive charge, a positive charge, a positive charge, a positive charge. Best example of that is a proton. And the third one, well, I'm not saying there is equal positive and negative. Those particles which have zero charge on it, actually no charge on it. Okay, example of that is a neutron. So a proton, electron, and a neutron are the best examples of the three categories of charges that you can get. Now, when I say zero over here, there is no positive and negative. It is actually nothing. Nothing is there on it charge wise. Mass wise, it is there, but charge wise, nothing is there. Okay. And you should obviously know the SI unit of a charge. The SI unit of a charge is nothing but a coulomb. A coulomb. Now, a coulomb is a very big unit. Usually, the charges around you will be in micro or pico or even nano coulombs. That's how small the charges around you are. But a coulomb is a big unit, but it is a SI unit of a charge. All right. And it is a scalar quantity. That means you can add and subtract them very easily. You don't have to worry about the direction. Yes. Okay. Sir is sweet 16 teaching with the same hype. Oh, thank you, Sanju. Sweet 16. That means I'm younger than you, I guess. Okay. Now, whenever I say that a body gets charged or his body is not charged, body is neutral, body is positively charged, what is negatively charged, what does it actually mean? Let's understand that. So let me give you a few examples of this. So that will make it absolutely very, very clear. So consider this multiple examples which I'm giving you over here. Oops. Okay. So consider this example where there are some positive charges here, some positive charges here, positive charges here. Okay. Look at all these bodies. Are you able to see those negative red icons and the positive green ones? All right. So the positive ones could be maybe the protons. The negative ones maybe are the electrons. Just chumma taking an example. Now look at the first example and the second example. Do you see the number of positive charges and the number of negative charges are equal? So they end up cancelling out each other. Perfect. Here, there are no positives and no negatives only. Nothing is there. Maybe it is made of neutrons. Who knows? Maybe this is a cloud of neutrons. Who cares? But there is no charge only on it. But both of them have a total zero charge, and that is why they are said to be electrically neutral. They are said to be electrically neutral. The only difference between both of them is here there is actually no charge or no charges on it. Here there are equal equal and opposite equal and opposite charges which cancel out each other to give you a zero charge on the body, to give you a zero charge, or basically making it electrically neutral. A human body, is electrically neutral because equal amount of protons and electrons are present. Everything around you is neutral, not because there is no charge, but because there are equal amounts of positives and negatives. If you consider this particular example, the positives are more, negatives are less. Maybe the electrons have ditched that, that solid or liquid or gas. So when there is more number of positives as compared to negatives, then it is said to be positively charged. Then it is said to be positively charged because there are excess positive charges. Positively charged. All right. So this is said to be positively charged. But when the number of electrons are more than the number of protons, then it is said to be negatively charged. Then it is said to be negatively charged. As simple as that. Till this point, absolutely clear. Give me a thumbs up. Give me a thumbs up or give me a heart in the chat box right away, right now. Yeah. Thank you so much, Sanju. Means a lot. Nikita, yes, definitely you can watch it, but there will be some concepts like vectors and Newton's laws which we'll be using. Yeah, correct. All right. Hi, Vasuki. Yes, perfecto, perfecto. Now that you understand it till here, what is the meaning of positive charge, negative charge? What is the unit? It is a scalar. Let us start seeing the main thing, which is the properties of charges. So properties of charges. By the way, usually the symbol that you use for a charge, the symbol that you use for an electric charge is capital Q or small q. Okay, anything you can use, capital Q or small q. The first property, there are three properties of charges. The first one is the additive nature of charges, and this happens since they are scalar quantities. Since they are scalar quantities, you can just add the charges. Meaning, say for example, there is a charge here, a charge here, a charge here, a charge here. Let's say this charge is Q1, this is Q2, this is Q3, this is Q4, this is Q5. And somebody asks you, come on, in this particular system, what is the total charge of that body? The answer will be just adding all of them with the signs considered. Q1 plus Q2 plus Q3 plus Q4 plus Q5. So say for example sake, there is a charge over here of plus 2 microcoulomb. Then there is a charge over here minus 3 microcoulomb. There is a charge here plus 5 microcoulomb. There is a charge here plus 1 microcoulomb. And there is a charge here minus 4 microcoulomb. And then we are asked what is the total charge on this particular body. You just have to add all of them, like 2 plus 5, 2 plus 5 plus 1 and minus 3 and minus 4. That's it. Just keep on adding everything over here that you see. So adding a negative number is just like subtracting it, right? Adding a negative number is just like subtracting it. So 2 plus 5 is 7, 7 plus 1 is 8, 8 minus 3 is 5, 5 minus 4 is basically 1. So 1 microcoulomb is the answer. So the total charge on it is basically 1 microcoulomb. Everybody understood? That is the first property. Because they are scalars, you just can add them. Lot of people have this question. Sir, if charge is a scalar, how come it has positive negative sign? Lot of students have this wrong misconcept in their head that if something is scalar, it has to be positive. Like mass, 2 kg, 5 kg, you don't have negative 3 kg. That is absolutely wrong. Just because something is scalar does not mean it can't have sign. It can be positive, it can be negative, but just that it is directionless. You cannot say charge of 2 microcoulomb in north direction. It has no meaning, no sense. So it is a scalar quantity. It is not a vector. Okay. I hope this is absolutely clear. No, not necessarily, Abhi, I'm not following necessarily H.C. Verma flow, but I would say I'm inspired from H.C. Verma's flow. I might deviate a little bit here and there, but you will see I love the way H.C. Verma sir, moves ahead with the syllabus. It's very, very natural flowing, right? Now, the next property is the conservation of charge. Next property is basically the conservation of charge, meaning you cannot, you know, create new total charge or or destroy the total charge. If you create some positive, equal amount of negative will be created to balance it out. So the total charge will always be constant. And not just that, it should be constant in an isolated system. What is the meaning of isolated? Meaning nothing can go out, nothing can come in. Just like your school, maybe very strict teacher. Anybody comes late, not allowed. If you want to go to the toilet, not allowed. Nobody goes out, nobody comes in. So an isolated system is where no mass, no charge, nothing goes out or comes inside. So in such a system, whatever is the total charge inside will be constant. So that is very, very important. So if you have some isolated system, you are doing some process and something happens, okay, in this particular process, maybe exchange of charges within that system. So if this is an isolated system, isolated system, and maybe there is some kind of process, whatever is the sum of the total charges initially will be the total charge which is there finally. This is what exactly the conservation of electric charge principle says. So whatever is the total charge initially will be the final charge eventually. So if you just take this particular example right over here, minus 10 is the charge on this rod. The sphere has 0 coulombs of charge. 0 coulombs of charge. Nothing is there. Nothing is there. Okay. So I can just put this is nothing but absolute 0 coulombs of charge. When you touch this rod, maybe some of the charge gets transferred. So if the rod is left with negative 7 coulombs, can you quickly guess and put it up in the chat box? How much charge is there on the sphere? I want everybody to put it up. Yeah, Pandu is going to come. Don't worry. Oh, my 2025 batch follower, I got VIT, AP, CSE, and under category 2, is it considerable? Siva, you can definitely consider it. Category 2, not bad. CSE, go ahead with it. And yes, AI ML is there. I mean, it's a very good branch, upcoming branch, and not to worry. Siva, go ahead. Okay. Yep. Right. So what is the answer, guys? Yes, the total charge has to be conserved. If the total charge is minus 10, here also it should be minus 10. So minus 7 when added with negative 3 will give you minus 10. Hence the answer should be negative 3 coulombs. Perfect. Not plus 3, negative 3, be careful. Yeah, minus 3, minus 3. Very good, Nikita. Nitika. Oh, we have two girls with this almost same name. Okay. Creative minus 3. Yep. Perfect. Similarly, let's say, for example, I tell you another example. Okay, maybe initially versus finally, I will show you two systems. Let's say there is one charge over here, 2 coulomb, another charge over here, minus 4 coulomb, another charge over here, 5 coulomb. Okay, like this. This is what is there initially. Now, what happens after some time? After some time, these people exchange charges with each other. Let's say this becomes negative 3 coulomb. This becomes 2 coulomb. So, can you guess what is the third charge going to be? Can you guess what is that third charge going to be quickly in the chat box, guys? This was 2, minus 4 and 5. This after something happens in some process, they exchange charges with each other. Can you guess what this charge is going to be? Well, add up the charges before. So it is 2 minus 4 plus 5. All right. So 2 minus 4 is basically negative 2. Negative 2 plus 5 is 5 minus 2, which is nothing but 3. That should be equal to Well, the total charge afterwards, which is -3 plus 2 plus whatever that question mark is. I don't know what it is. So -3 plus 2 is nothing but -1, and that question mark still remains. Solving this, what are you going to get? -1 goes on the other side. So the question mark will be 3 plus 1, which is basically 4. So that unknown charge over here will be 4 coulombs. Will be 4 coulombs. Understood, guys? Everyone? Very good, Vignesh. Akshara, Siddhi, Siddharth, Saibu, very good, Nitika, Sneha, awesome, awesome, perfect, perfect, amazing. So that is nothing but conservation of charges in isolated systems, useful in many, many problems. These are looking very simple, but it will be useful as concepts for complex questions. And then you're like, oh, yes, charge is conserved. Oh, yes, charge can be added. Oh, yes, quantization of charge. This is the third property. So what is this third property? Quantization. Example. Okay. Shreyas sir. Shreyas sir has Shreyas sir has these 100 rupee notes. Only hundreds. In my pocket, in my wallet, everywhere, only hundreds. Okay. Only 100 rupee notes are there with Shreyas sir. With this 100 rupee notes, can I make 2,700 rupees? Is it possible? Yes or no? Come on, quickly put it up in the chat box. Thank you, Durai Kanan. I'm not really sure, Vignesh, if there is quantum computer in IIT Madras. That's a very specific question. Yeah, this is definitely possible. I can get 27 notes of 100 and I will get 2,700 rupees. Definitely possible. Can I get 500 rupees using these 100 rupee notes? Yeah, I can get 5 notes and definitely it is possible. Can I get 750 rupees? Can I get 750 rupees? Is it possible using these 100 rupee notes? No, right? It is not possible no matter what you do. Can I get 58 rupees using these notes? 58 rupees using these notes. You cannot say, sir, one note, no, at exactly 58%, I will tear it. So whatever is remaining is 58 rupees. You will get one tight slap. So this is not possible, right? Can I get 1 rupee? No. Can I get 2 lakh 58,300 and or 300 maybe rupees? Definitely, this is possible. This is definitely possible. 2,58,300 is possible. But anything which is not a multiple of 100 is not possible. So here I can say the money that I can transact with is quantized, meaning you cannot have any value. It has to be in multiples of a peculiar number. In this case, the quanta of money that I am using, quanta is 100. This is my quanta. That is the smallest number I can use. I cannot go below this, but anything above it will be a multiple of it. So the money is a quanta of 100 rupees, I can say, in my specific example. Somebody might have only 500 rupee notes. So for that person, he cannot transact with 2,700. For him, it will not be possible. But with 500, you can transact this. You can't transact this, nor this, nor this. But even this is not possible with 500 rupee note. So basically, even charge is quantized. Even charge is quantized. And Millikan found it out with his experiments that the smallest quanta, the quanta of charge, the quanta of charge, the quanta of charge, which is basically the smallest magnitude of charge, the smallest magnitude of the charge. This is basically E, and E has a very specific value, which is 1.6 into 10 to the power negative 19 Coulomb. So this is the smallest magnitude of the charge which is possible. So if you have any other charge, let's say Q, it will be multiple of E. So E has to be multiplied with N, but it can be positive or it can be negative, where N is any, let's say, natural number like 1, 2, 3, 4, like that. It can be any natural number. So Q will be equal to N times of E. N is any integer which is positive, let's say 1, 2, 3, and you can put plus and minus, or you can just say n is integer, then plus minus is not needed. Okay, is this absolutely clear? Yes, you can definitely do both 11th and 12th. Both classes are backlogs. Definitely you should do both of them together, especially if you're a dropper or class 12th with 11th standard backlogs. Okay, GA aspirant. So let's say I give you certain examples like which of these charges are possible, which of these charges are possible, which of these charges are possible. Okay, first one, 3.2 into 10 to the power minus 18. Second one, 3.2 into 10 to the power minus 19. Third one, 4.8 into 10 to the power minus 17. Fourth one, 5 into 10 to the power minus 19. Fifth one, 8 into 10 to the power minus 3. Okay, so these are the values that I have given. You think and tell me which of them are possible because of the quantization principle, and some of them will not obey the quantization, so they will not be possible. Just think about it. Yeah. Is 7th a good year to start? Ayo, Vignesh, chill, bro. 7th is a good year to start foundation, not J. J you can start it at 11th only, but you build your foundation and basics, like take part in NSCJS, Olympiads, okay, hackathons, develop the coding skills, learn communication skills, learn the languages, learn maths, learn science, learn sports, build your personality, learn games, everything. So build that up in 7th standard, okay? Or maybe whatever is your interest. If maybe chess is your interest, build up that, okay? But no need to start JEE in 7th standard. You just need to start foundation. Yeah, this is important. 2 years is more than enough otherwise. Yeah. Well, as you can see, if Q is equal to N times of E, this means N is nothing but Q by E. Q by E. N is nothing but Q by E. Over here, if you just try to figure out what the value of N is, the value of N is charge, which is 3.2 into 10 to the power minus 18, whole thing divided by 1.6 into 10 to the power minus 19. Well, 3.2 by 1.6 is 2, minus 18 minus 19, that will make it 10 to the power minus 1. Is that right? And take it on the top, take it on the top, this will become 2 into 10 to the power 1, which is basically 20. That means this is definitely possible. So 20 of them are needed. So definitely one is possible. If you talk about the second one, 3.2 into 10 to the power minus 19, this is anyways seen that this is nothing but 2 multiplied by 1.6 into 10 to the power minus 19. Or if you don't like it that way, let's just count it simply. How much is the integer value? So 3.2 into 10 to the power minus 19 divided by the charge, which is 1.6 into 10 to the power minus 19. So minus 19 cancels. This is becoming 2. So 2 is an integer. Definitely it is possible. Is that right? What about this? What about this, guys? Let's check it out. 4.8 into 10 to the power minus 17. Again, I think this is possible, guys. Just check it out. N is equal to 4.8 into 10 to the power minus 17 divided by 1.6 into 10 to the power minus 19. So 4.8 goes with 1.6 three times. This will become nothing but 10 to the power minus 2, which is 300. And 300 is an integer. So definitely this is possible. What about this? I doubt this should be possible. Like N is equal to, so 5 into 10 to the power minus 19 by 1.6 into 10 to the power minus 19. So this will be 5 by 1.6, and 5 by 1.6 is not an integer. It is not an integer. It is not possible. Okay, it is not equal to 1, 2, 3, 4. It is not any integral value. So not possible. What about this? This also, guys, you can see 8 into 10 to the power minus 3 divided by 1.6 into 10 to the power minus 19. Is that right? Yep. 1, 2, 3. So fourth is not possible. So let's check this out. So 8 by 1.6, just you can write this as 80 by 16. 80 by 16. by shifting the decimal. This is minus 3 will cancel. So 1 by 10 to the power minus 16. So 80 by 16 is basically 5. And this goes on the top. So 10 to the power 16. So definitely this is possible. It's a huge number, but it's an integer. So this is also possible. So the fourth one was not possible. Yeah. Fifth one is possible. Got it? So some of you missed the fifth one, I guess. Some of you missed the, something else. Maybe the fourth one, maybe you got it wrong. Yeah. So this is how you do it. So you just have to see whether when you divide charge with electron charge, whether you get a numerical integral value or not. If you get, it's perfect. If it is not, it is not possible. So before going ahead, we all should also appreciate the fact that you should know this, that when you have positive and positive, or positive over here, this is negative and negative, and this is negative. So whenever you have positives like this, they will tend to go away from each other. They will basically repel. And whenever you have opposites, they will tend to go towards each other. Basically, they will end up attracting each other. So you should know this basic property of charges. Okay. So I'll just highlight this. This is repulsion and this is attraction. Okay, everyone? Cool. So let's have a look at some questions coming up on your screen, and here it is. We have a soap bubble. Everybody would have seen a bubble. Soap bubble. You might have seen it in some fair or some, I don't know, anywhere. Maybe you would have made it using your bathroom soap also. You can make it very easily. Yeah, a soap bubble is there. It's a thin layer of a soapy, filmy liquid. Okay, and it is given some negative charge. Imagine the negative charge is on that shell of that soap. Then what do you think will happen once you give that charge? Will the radius increase, decrease, remain same, or what? Yes, perfect. What do you think is the correct answer for this? Nitika saying B, increases, decreases. Oh, by the way, do you think the answer will be different if instead of negative, I give positive charge? Then what do you think the answer will be? Then will it decrease or will it increase? Then will it decrease or will it increase? Creative thoughts, the lecture will be anywhere between 1.5 hours to 2 hours, 15 minutes, anywhere between that range. Okay, already mentioned during the launch. Yep. No, Namneet, we have created a much better version of Jungle Book. After every lecture, in the description box only, now that link will get added of the comment section. So, of the PDF. And we'll make playlist of all our lectures on the homepage. So you don't have to click any other link, go to any other sheet. Last year, probably we were figuring out things, how we can put the PDFs, everything. So now, the best way is we have our own server, Amazon server we have, and on that we post everything. So you just have to click the link which is there in the description or in the comments after the session is over. Yeah. So the answer for that is increases, irrespective of whether it is negative or positive charge. It really doesn't matter, my dear students. See, imagine this was negative, 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 negative. Okay. And let's say this was positive, 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 positive. What will the negatives do? I just told you over here. Negative with negative will repel, positive and negative will attract. Okay. So that means over here, these negatives will all end up what? Repelling each other. They will end up, this negative will be repelled by that, this, repel. Even these positives will end up repelling each other. So because of that repulsion, the repulsion causes that expansion. Repulsion will cause that expansion. Repulsion will cause that expansion. So it doesn't matter whether it is negatively charged or positively charged, the answer will be the radius will increase. Is this absolutely clear? Yep. Yes. Awesome. Yes, Arihant is a good book, man. Don't worry. All right. Moving on to the next question. If 10 to the power 14 electrons are removed from a neutral metal sphere, the charge on the sphere becomes. So imagine there was a neutral sphere and you took away some electrons. Okay, you have taken some electrons, away. So if you take electrons away, what will happen? The sphere will 100% become positively charged, isn't it? The sphere will become positively charged because electrons are gone. Earlier, it was an electrically neutral sphere. It was neutral sphere. So when you take it out, obviously positive charge will remain. So obviously certain answers are wrong only. Like B option can't be correct. Even D option can't be correct. Got it? B and D are eliminated. It can't be negative. So it has to be either A or C. It has to be. Very good, Nikita. Correct. So, but you cannot decide like this orally. So you have no other choice but to solve it properly. So the charge on the sphere will be the number of charges that you have taken into the electron charge. Okay, magnitude wise. So n is nothing but 10 to the power 14. E is nothing but 1.6 into 10 to the power minus 19. So this will become 1.6. 19 minus 14 is basically minus 5 over here. So I want micro, right? So 16 into 10 to the power minus 6. Deliberately, I shifted the decimal. So I increased the negative power of 10. So this is 16 micro Coulomb. So 16 micro Coulomb is the magnitude of the charge which will be there. But I know that charge has to be positive. So therefore, it should be option A. Okay, this is just the magnitude. If you actually talk about the value, it will be plus 16 microcoulomb, right? That is the positive charge which will be remaining. Is this absolutely clear, my dear students? Yes, perfecto. Let's go ahead to the next thing. Now, 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 let's talk about the different ways in which you can charge something. And for that, let's understand conductor and an insulator. Let's understand conductor and an insulator. Yes, yes, Siri, you can crack JEE 26 by covering the 11th backlogs. That's why we have kept the 11th standard classes at 6 o'clock. You can watch that, and after that, 8 o'clock, watch the 12th standard classes. You always have the option to, watch our older recordings of Roar or maybe Nurture Pathfinder. Feel free to watch them as well. But the latest new pattern concepts and problems will be done in this particular series. Okay, so now, what is the difference between a conductor and an insulator? Conductor conducts, insulator insulates. From what? From electricity. As simple as that in layman terms. That's what you learned in your school, 8th, 9th standard. So a conductor basically has free electrons. A conductor basically has free electrons that can mobilize. Mobilize means they can move. So something is mobile means they can move. So mobilize means they are able to move. So they can mobilize when potential difference is applied. Potential difference is applied. Now, when you say potential difference, looks like a very complicated word. It means you connect a battery. A battery has positive and negative. Positive is high, negative is low. So that's a high minus low, which is a potential difference. You connect a battery and you will see the electrons will mobilize themselves, and it conducts electricity, and it conducts electricity and electric current. Best example of conductors: copper, silver, gold, aluminum, right? All these basically metals, all these metals are usually good examples of conductors. Metals have those free electrons which they can easily conduct. So that's one special property. Insulators, due to the absence of free electrons, they can't mobilize charges and can't conduct What can't they conduct? They can't conduct electricity. They are bad conductors of electricity. A lot of examples are there for insulators, like you have your rubber, you have wood, you have plastic. So many things are there around you which are bad conductors. They are insulating in nature, like the shoes that you wear, the rubber slippers, the wood, the plastic, the so many things are there which are bad conductors. Okay. Now there is a separate chapter which will come later on in JEE and towards the end, that's semiconductors. Those are special kind of solids where it is better than an insulator, but not as good as a conductor. So somewhere in between, that is called as a semiconductor. Okay, we'll talk about it separately. For now, just understand these two things. Now, why are we discussing about conductors and insulators? Obviously, we are talking about charges, and charges will flow here and there. So when charges will flow here and there, it depends whether they can flow or they can't flow. So that decides whether something can be charged or not charged, and how much can it be charged, etc. There are multiple ways of charging, and I will show you all of them. So for that, let's open up FET over here and go to the one of the best simulations out there for physics, chemistry, maths, everything, guys. It's a very nice tool. Yep. So let's go to, what is it, electricity and charges, and let's go to this dude out here. So there are three ways in which you can charge something. There are how many ways? Three ways in which you can charge something. Yeah. This is not one shot. These are separate lecture series, lecture 1, 2, 3, etc. Every lecture we do some subtopics from a chapter. Yeah. Okay. Perfect. Sir, can you make a video on physics Olympiad info, as I want your expertise guidance? All right, Pratyush, fair enough. Okay, definitely. Now, see, you might have experienced some kind of shock, electrical shock, when you touch someone or touch a doorknob or touch some metallic railing. Have you experienced it? If you have, put up a shocked emoji in the chat box. Yeah. Have you experienced that? Definitely you would have experienced it. So why does that happen? So let's understand it. The first method and the second method of charging is there in this demonstration itself. When you rub two things, what will happen? The electrons which are revolving around the atoms, they get rubbed against each other. They will collide. And once they collide, what will happen? If you rub it hard enough, they might get knocked out. But who decides which electron will get knocked out? Well, if there are two surfaces which are rubbing, then the surface which loves the electrons more will pull the electrons from the other guy, and there will be one surface which will not like the electrons so much. So it depends essentially on the electron affinity of that particular solid, liquid, gas, whatever is being rubbed. So the object which loves, which has more affinity means liking towards the electron, will pull that electron. The object which has less affinity towards the electron will lose the electron. So when you rub things, you will see one will become positively charged, one will become negatively charged. Like for example, this person is walking on the carpet flooring, and as he walks, you can see some negative charges are entering the human body. What is this, guys? Who loves the electrons? The person or the carpet? Does the person, that clothing of the person, love the electrons more, or does the carpet love it? Obviously, the person, the clothes that is wearing, they love the electrons. So that is why the electrons are getting pulled. But maybe the carpet does not love the electrons as much as the clothes or the person does. So it loses the electrons in this battle of collisions. It's like two sheep or two animals banging onto each other, and one of them loses their cool or loses something. Yeah. So the electrons are now over here. Fair enough. This is first way of charging. This is called as charging by rubbing or friction. What is this first method called? This first method is called as charging by rubbing. Okay, so now you have rubbed your foot against that particular another surface. You got charged. One is negative, one is positive. Always equal and opposites will be developed. Now this person right now, let's say he's putting his hand in the nose. After some time, maybe he is satisfied or whatever, and now he feels like touching that particular doorknob. Please don't touch the doorknob, it will have lot of virus because his hand was in the nose. Am I audible now? Am I audible? Am I audible? Am I audible? Am I audible? My battery went off, looks like. Now is it, now is it audible? Now is it audible, guys? Yeah, perfect. Vignesh, Nigam, Ibu, Nikita, Nitika, Shins, Praveen, Navneet. Is it audible now? Yes, perfect. Okay. So human body is a decent conductor of electricity. Decent conductor of electricity. It is not very good. It's not very bad. Correct? Right. It's not so good that we use human bodies to connect from one socket to one light bulb. Sir, I've used human bodies to conduct electricity. That will be very evil, very dark. Oh my God, this guy looks like he has got pimples and this guy's hand is still in his nose. Anyways, now human body is a conductor. The doorknob is also a conductor. It is metallic in nature. When two conductors touch each other, one of them has charge, one of them does not have charge. What will happen? Conductors will conduct. One of them has charge. This guy will feel jealous. This guy will feel left out. He will get FOMO. He will be like, hey man, give me charges. Immediately the charges will flow. So the moment this dude takes out his hand from his nose and touches it, see, zip, all the charges went over here. Yeah. So this is basically the second method of charging, that is called conduction. This is called conduction. Everyone with me? Understood? Yes. Hi Divya, welcome aboard. Yes, perfecto. So this is charging via rubbing. Oh my God, it is getting conducted because his hand is touching it. So he rubs his hand and there is a conducting path. But if it is not, then that's it. The charges stay. The moment there is a conducting path, the charges will conduct. That is the second method of charging. Is there a third method of charging? The answer is yes. Let's go to look at that as well. After that, things will be very, very clear. So see guys, seeing practically things make a lot of difference. So we have balloons example. Oh, what are these? This is a sweater or cloth balloon and this is a wall. Okay, if you don't want the wall, let's remove the wall. You want the wall, we will add that wall. Okay, now ideally all of them have no charges. They are all electrically neutral. That means they have equal amount of positives and negatives. So they are all electrically neutral. Is that right? Let's go back to our first method of charging. What was that? Rubbing. Yes. So let's rub. Oh my God, what just happened? That sweater lost the electrons in that battle to the balloon. The balloon had greater affinity towards the electrons. It pulled those electrons. Look at it again. The balloon, when rubbed on that sweater, it pulled those electrons onto it. So this is the first method by rubbing action. Is that right? I can rub more and I can suck out even more charges from it. Oh, very good. Now the balloon is negatively charged. Is it right? The balloon is negatively charged. So now comes the third method. Now the third method is true for insulators. It is also true for conductors, but for insulators also, you will see that it is valid. Okay, observe this. Wall is an insulator. Ideally, it will not conduct electricity. So, if I even, for example, if I even touch the balloon, nothing will happen. I mean, no charge will go onto it. The balloon will not lose any charge. I mean, if I see it also, the balloon will still have it. Because this is an insulator, rubber is also an insulator, charges will not go from here to here. But see one interesting thing which happens when I bring the balloon close by. Are you seeing the electrons in that wall running away from the balloon? Are you able to see that? Yes or no? Let me know in the chat box. Yes, sir, I am able to see it running away. See, when I bring that balloon close, the electrons are running away. This is called induction of charges. What is this called? This is called induction of charges. I mean, why balloon has more affinity? That is chemical reason. When it's like you study in chemistry, why something has more electron affinity, why something has less electron affinity. That depends on the composition, compounds, elements, electronic configuration. So many things are there. Okay, let's not get over there. It has more, it does not have more. So that's all we are bothered. So you can see the electrons running away in the wall. This is called induction. So this side of the wall is exposed now. It becomes positively charged. This side, more concentration of negative. This becomes negatively charged. This process is called induction, where without touching, you create charges. Without, I have not even touched. This is positive, this is negative. This is called induced positive charge. Okay, it is induced positive. This is called induced negative charge. So we have now created one side of the wall positive, another side of the wall negative. We have created two different polarities, poles, positive pole, negative pole. So I say that the wall is now polarized. I'll say that the wall is now polarized. Polarization means you create differences, you create poles, you create one thing opposite of the other thing. So right now there was no polarity. Everything was smooth, 0, 0, 0 charge. But the moment I bring this here, now there is polarization. This is positive, this is negative. It has been polarized. This is positive induced, this is negative induced. Is this now clear, everyone? Yeah. Today we will not complete electrostatics. It will take 2-3 weeks. Electrostatics is one of the biggest chapters. One of the biggest chapters. Electrostatics, magnetic effects of current, ray optics. These are like the three big chapters of 12th standard, right? Okay. So let's have a final conclusion over here. When you say charging by friction, so say for example, here you basically rub them, so that's why these arrow marks, you are rubbing them. And then I see that after rubbing, maybe this became positively charged. So an equal amount of negative charge will be there. So this has more electron affinity. This has, I would say, less electron affinity. Affinity means liking. So when you rub in this particular process, you will see in this process, I will say after rubbing, in this rubbing process, equal and opposite charges are developed. That is one thing. Most importantly, is it the positive charge that jumps from here to here, or is it that the negative charge which jumps from here to here? Answer the question. Which actual charge goes from one body to the other body in this rubbing process? Come on. If Earth is neutral, why does it attract charged objects? We'll come to that, Pratyush, when we discuss about earthing. Okay. Earth is a decent, okay conductor. Modern physics is towards the end. All right. By the way, I started modern physics in our Sigma batch. Sigma JEE 2026 pure English batch, we have already started modern physics, right? Yeah, it is the negative charge which flows. Correct. Always remember this. It's the negative charge, meaning the electrons which ditch the atoms, leaving these positives alone, single. So these negatives ditch them. So it is always the electrons which jump the bodies, which jump the bodies from one to the other. Protons, which is a part of the nucleus does not move. It's the outermost electrons which usually transit and they get knocked out from one body to the other body. This is what you should know. Next important thing, conduction. This can only happen in conductors. So there is a transfer of charge between two conductors, specifically between the conductors between the conductors by touch. That means touch, or basically a conducting path, either one of them. So like you can see, there was a sphere. Okay, you take a charged rod and you touch that sphere, automatically the charges will jump onto the sphere. So the sphere will become charged. Or another example will be, you have one body over here and this is another body, and this is another body. So right now, let's say there was positive charges over here. What you do is you connect a wire. You connect a wire between them. The moment you connect a wire between them, immediately what will happen? The moment you connect a wire, you will see these charges which are there over here. They will begin to flow. There will be flow of charges, and eventually you will see the charges will get distributed like this. So there will be an equilibrium which will be achieved later on, but the charges will definitely flow through that connecting wire or the conducting path, and there will be an equilibrium which will be achieved. So this is again charging via conduction. You conduct the electricity via a conducting path. That is very, very important. This is absolutely clear. By touch, or better word for that is conducting path. Conducting path via a conducting path, which usually is a touch. You are touching those wires. Okay. The third one is charging via induction. Where charges equal and opposite are induced due to the presence of external charges, and all of this is without touching, no need of touch, and this can happen in conductors or insulators. This can happen in both conductors as well as insulators. So charges are going to get induced. This process which creates induced charges, that is also called as polarization. So polarization will happen. Polarization of the body will happen because of induced charges. So if this was that particular body, you will see one side might become positively charged, the other side will become maybe negatively charged. So this is basically polarization. The charges are separated, so that is why it is being polarized. I will give you best examples of both of them. This is very, very important examples, guys. Please take a note of it. Okay, observe this very, very carefully. Observe this very carefully. Okay, whatever I am going to do now. There is a conducting sphere. There is a conducting sphere. This is basically a conducting sphere. This is a conductor. Right now, it is neutral. Right now, it is perfectly electrically neutral. Now, what you do is that you, for example, get a positive charge over here, close by, somewhere over here, you get a positive charge over here. What do you think will that positive charge do to the conductor? Think very carefully. What will that positive charge do to that particular conductor? Which is strong, conduction or induction? Conduction is strong as compared to induction. You will see now why also in a moment. This is uh, induction. We are not even touching it. Yes, the conductor is made of positives and negatives. Who will be pulled now? Yes, electrons. And can electrons move inside a conductor? 100%. So you will see that the electrons probably might leave their original atom and might reach over here. Might leave their original atom and might reach over here. Might leave their original atom and might reach over here. So this side might become negative. So if they have left their atom and come on this side, obviously this will be positive, this will be positive, this will be positive. So this is induced positive, this is induced positive charge. This was not real charge, this was induced by this charge. This is nothing but induced negative charge. And as you can see very clearly over here, this has been polarized. This has been polarized. Everybody clear till this point? Everybody clear till this point? Yes. What would have happened? What would have happened if instead of the positive charge, I had brought negative charge over here? If I had brought negative charge over here, then you would have seen that these electrons from these atoms would ditch them and they would go over here. So maybe this will be negative, this will be negative, this will be also negative, and a positive charge would have developed over here. Isn't it fascinating? It will develop opposite charges, but now this side, the closer side will be positive, the farther side will be negative. If you bring positive, the electrons will get pulled, and this side will be negative, that side will be positive. Anyways, it gets polarized. Is this clear? Now, let's do the same thing with an insulator, because a lot of people have this misconcept. So let's have a look at that. So let's say the same thing, but this is nothing but an insulator. Right now, the insulator is perfectly electrically neutral. That means equal amount of protons and neutrons. So this is neutral. Now what I do is I bring a positive charge over here. What do you think will happen? See, earlier it was a conductor, all the electrons jumped, left their nuclei, and they went closer to the positive charge because they got pulled by it. What do you think will happen to the insulator? Lot of you might be thinking, sir, it's an insulator. The electrons can't move, so it will remain as it is. Nothing will happen. Well, partially you are correct, but something will happen. Something will happen. Guess what? See, if you zoom at microscopic level and concentrate on that atom will have this nucleus at the center. This is positively charged, and you will see that the electrons form a cloud. The electrons form basically a cloud around the positive charge. An electron cloud is there around it. So because of that, what happens? The positive and negative centers coincide. So in this case, the positive and negative coincide. The electrons are spinning zzz, and the negativity and the positivity is at the same place. But the moment Just think about it now. Just think about it. The moment you have a positive charge here, I feel that electron cloud only will get distorted. Yes, the electron cloud only will get distorted and most likely it will look like this. Just visualize this now. The electron cloud only will get distorted. It will probably look like this. I'll just try to draw it as much as possible. Like this, visualize. So that electron spends more time over here. It's like, imagine there is a beautiful girl in some section 2. So this Pandu who is there, that Pandu will move more and more towards section 2. Yeah, it might have happened with you also. If there is nothing, everything is chill, then you are in your class only. Okay, in my class only, I'm moving around. Some beautiful girl is there in some other classroom. So what will you do? You will move more towards that. So that is what is happening to this electron cloud. It loves this positive charge, so it is coming close. It can't leave the atom though, because it is an insulator. So the negative center, there is a delta negative over here, and now there is a small positive over here. So the atom itself gets polarized. So the atom is basically polarized. The atom itself is basically polarized. Understood, guys? Everyone? Yeah, perfecto. So here also what happens is you will see that delta negatives everywhere will be formed closer to the positive charge, and the delta positive will be formed farther from that positive charge. If instead this was a negative charge, then you would have seen that the positives will be closer to it, the positives will be closer to it, and the negatives will be farther to it. So this is how the centers will move. I mean, the overall positiveness will be on one side, overall negativeness will be on the other side. Is this absolutely clear? Yeah, perfect. Yes, the charges get separated at the atomic level. But in case of a conductor, the electrons ditch the electrons ditch the atoms and move, jump to the other thing. So it's like some beautiful girl is there, no teacher in the class. That Pandu left that classroom and went into that other class and sat there on that same bench with that beautiful girl. That is what has happened. That is what happens in a conductor. Is this absolutely clear, my dear students? Perfecto. Okay. Awesome. Awesome. Clear? Now you understood the difference between the two. Now I have a very important question for all of you. Do you think this conductor, which was neutral, will get repelled or attracted by the positive charge? Conductor was neutral. Do you think it will get attracted or repelled by the positive charge? Come on, think about it and answer in the chat box. Think, guys, carefully. This was the positive charge. The positives were here. These are the negatives of the sphere. Well, these negatives which are there, these negatives will get pulled, these negatives will get pulled by the positive charge by a good amount of force because it is closer, because of the proximity. But at the same time, this positive and this positive will repel, but with not so much of force. Decent amount of force only will be there. Out of the two, who will be stronger? I think the attraction will be stronger. There will be strong attraction. There will be strong attraction, and there will be weak, weak repulsion. So as a result, what will be the net force on it? What will be the net force on it? Yes, the net force will be in this direction. So the net attraction will be there. Net attraction will be there. Is that absolutely clear? Because of the proximity of the negative charges and the positive charges with the positive are far away, so it will be weaker. Yes. So lot of people think it will neither attract nor repel, but that can be the tricky question in JEE which can be asked. And many people will think nothing will happen, but the actual answer will be net attraction. Can you similarly guess what will be the answer for this? Can you similarly guess what should be the answer for this particular thing when you take a negative charge over here? When you take a negative charge over here, this will be positive, and of course, this will be negative. Now, again, think logically. Who will be stronger? Who will be weaker, etc. Negative, negative will repel, but it will be very far. So it will be very weak repulsion, very weak repulsion. And if you see the positive charges out there, well, positive and negative will attract by a strong force. Definitely, this forces will be strong. So there will be a strong attraction, strong attraction. So as a result of this, 100% there will be attraction again. A lot of people think it will repel now. No, it will still be attraction. So there will be net attraction over here. Is this absolutely clear? Yeah, even this will attract. So a lot of people think neutral conductors won't get attracted, but neutral conductors can get attracted to positive and negative charges. Okay, but never will it repel. In no scenario will it get repelled. Is this absolutely clear, everyone? Perfect. Now let's see whether you can answer this for a insulator. What do you think for an insulator? Will it attract or will it repel? Will it attract or will it repel? Think carefully. Over here, every negative charge is closer to the positive charge. All the negative deltas are closer than the positive deltas. That means the attractive forces between negative and positive, attractive forces are slightly, definitely more than the repulsive forces on that positive charge. So what will happen because of this? There will be definitely some attraction, but this will not be as good as a conductor's attraction, because here the difference in the distances was huge. This is very close, this is very far. So the difference of force, like if the attraction was 5 Newton, the repulsion was 1 Newton. So the difference was 4 Newton because of the difference in the distances. Here, the difference in the distances is not much. So the difference of the forces is also not much. If the attraction is 4 Newton, the repulsion is 3.9 Newton. So, it is not much of a difference, 0.1 Newton difference. So there is a small attraction. And the same logic can be also used over here. So there will be again some kind of small attraction over here. And it can be very well seen even in this example out here. Look at this. This is an insulator. In spite of that, the balloon is sticking. See this? Balloon is sticking to this. Why is it sticking? Because this negative charge is being pulled by the positive charge strongly, and it is repelled by the negative charge weakly. So there is an attraction between the wall and the balloon. But if you bring the balloon here, it goes here. Because the balloon has a negative charge, the cloth has a positive charge. So obviously they will end up attracting each other. So that physics has been simulated very well in this particular simulation. So is this clear? Even in an insulator, attraction happens, but it is not as strong as the attraction in case of a conductor. If you have understood it, please put up a heart or a smiley or some fire emoji in the chat box. Everybody. This is one of the most important things in this rubbing, conduction, induction, etc. All right. Next question coming up on your screen. Ready? Ready for the next question? Ready for the next question? In this example of conduction, the mass of the blue one, the mass of the blue body will increase or decrease? Answer in the chat box. The mass It is negligible. Yes, the force is negligible, but it is still there. That small force of attraction is still there. Okay. Come on, everyone. This blue body, this particular blue body, think about it and tell me. Think about it and tell me. Will it increase its mass or reduce its mass? If you answer this, I would be super duper proud of you. Well, see, the positive charges have flown, but I have told you before also, the positives never actually move. Yes, it net charge is moving positively, but actually what is moving is the electrons. So if the positives have gone here, meaning there are some electrons which moved along that wire and jumped onto this positive. This electron also jumped onto this positive. They nullified this positive. And because the electrons left, they have ditched their atoms. That's why this side becomes positive. So if electrons leave this conductor, that means the mass will become less. So the mass reduces slightly. So the mass reduces by a very small amount. Yeah, it is very small. It is not in kgs or grams or even milligrams. It is very small because what is the mass of an electron, guys? It's like 9 into 10 to the power minus 31 kg. It's extremely, extremely small. But that difference is definitely there. It decreases. So whose mass increases? Obviously, if the electrons have transited, they have added onto the mass. So here the mass increases. Here the mass increases. Here the mass increases. Perfect. Yeah. Cool. Understood. Let me ask you the same thing over here in case of polarization. Take this example. Do you think the mass of the conductor will increase or decrease? In case of induction, will the body being induced with some charges, will the mass increase or decrease in this case when the positive charges got over here? Come on, think about it carefully. Yeah, will it increase, decrease, or not change? Yes. Has the electron been brought from outside? No, right? This electron was already present within the body. It has just moved from one side to the other. It's like you are in a bus and from the back seat you have gone to the front seat, or from the front seat you have gone to the middle seat. Something like that. So there is no change in the mass. Correct. There is no change in the mass, in the net mass, but the mass gets redistributed within that particular body. You can see that the negative charges go here. So this side will become slightly heavy. The right side will become slightly lighter. So if the body was perfectly balanced, because the electrons moved, it's like all the kids from the back seat came onto the front seat. So, the bus will become unbalanced now. So this body will be heavier slightly on this side and lighter on this side. Is that clear? So this kind of thinking you should have when you're thinking about JEE. Okay, at the minutest of the minutest level, okay, at the microscopic level to the macroscopic level. What is happening exactly in conduction, induction, everything you should know. Cool? Yeah, total mass will be conserved, but the mass distribution within the body will definitely change. All righty, perfect. So moving now to some question. I think this question just got repeated 2 times. Yeah. There is a polythene piece which is rubbed on wool, which has a negative charge of so and so Coulomb. Electrons mass is so and so. The mass transferred to the polythene is how much? See, there is a polythene piece which is rubbed with wool. It has a negative charge of negative 3.6 10 to the power minus 19. So if there is a negative charge on that body, obviously it would have come because of excess electrons. So how many electrons came? If you find that and you know the mass of each electron, you can find the total mass being transferred. So first job is to find out the number of electrons. And we know the number can be found out easily. The number value is charge by E by quantization principle. The total charge on it is 3.6 into 10 to the power minus 7. Electron charge is 1.6 into 10 to the power minus 19. Okay, this is the number of the this is number of electrons transferred, number of electrons which are transferred. So now if the question is what is the mass of the total mass of the electrons, that will be the number of electrons into mass of each electron. The mass of each electron is already given to us. So number is nothing but 3.6 into 10 to the power minus 7 divided by 1.6 into 10 to the power minus 19. The whole thing into mass of the electron, which is basically 9.1 into what is it? 10 to the power negative 31. If you want, you can just shift the decimal a little bit and solve it, guys. It's not that difficult. So the 16 by 4 is 4. 36 by 4 is basically 9 over here. So we have out here 9 multiplied by 9.1 divided by 4 multiplied by minus 7 and minus 31 will make it minus 38. Minus 38 and minus 19 over here. So I am left with 10 to the power minus 19 on the top. That's it. So this much will be the mass. So 9 into 9 is 81. And we just divide, basically 9.1 into 9 is almost like 81 only. And you just have to divide it by 4. So 80 by 4 is 20. So 81 by 4 will be 20 point something. So approximately, if I say, it will be 20 point something, okay, something into 10 to the power minus 19 kg. But I can see over here, 2 point something. I can see 2 point something. So definitely it will be, 2 point something into 10 to the power minus 18 kg. So basically it will be option C. Perfect. Option C. Yeah, perfect. Is that clear? How we got it? Yeah. You need not have to sit and do the exact calculation. Okay. How many PYQs required from each chapter? As many as it is needed for confidence building. For big chapters, you might need many PYQs like rotation, electrostatics. For small chapters like fluids or solid mechanics, you might just be okay with some 30-40 PYQs also. Yeah. Right. Perfecto. Let's go ahead now to the next part, which is basically our Coulomb's law. Okay, let's see this. Okay, let's see what is our Coulomb's law. And then we'll see also superposition. Ready for it with full josh, full energy, guys? Coming up on your screen, here it is. And I hope you have smashed the like button. In case you have forgotten, just reminding you, okay? That is the way in which, manner in which you mark your attendance. If you have two charges, they will either attract or repel each other. They will either attract each other or they might repel each other depending on their signs. If both are positive, repel. One is positive, one is negative, attract each other. Is that right? Yeah. Tattva is enough along with PYQ books. That's decently enough. But if you need more advanced questions, we have Rank Accelerator and all of that. But for beginners, till medium and decent level, Tattva and PYQ book is more than enough. Yeah. Now, Coulomb said that, here is Coulomb's law. Coulomb's law. He said that the force of attraction or repulsion is along the line joining the charges. Now, this might seem like a very natural thing to you, but it is not so natural when you see magnetism. Like, see, this is the line joining the charges. So the force of repulsion or attraction will be along this line. That's what he said. But you will see that there are some chapters where the charge is moving somewhere. The force is in some weird direction only. So why is the force not perpendicular? Why is the force not in some angle? Okay, there is no reason for it. This is just a law. So the force either is away or towards, but always along that line joining the charges. You will never see it making an angle between the charges. So this force I can call it as F. Yes, this force I can call it as F. And the second point that he mentioned was that the force is proportional to the product of the charges. The force is basically proportional to the product of the charges and inversely proportional to the square of the distance between them. That is the reason why it is also called as a square inverse square law. If the distance increases, the force reduces. If you bring them close, R will reduce, force will increase, it will become more strong. If the charges, both of them are very high value, the force will be very strong. One of them decreases, the force will reduce. The other decreases, again the force will decrease. So it was proportional to the product of their charges. So then he said, okay, so therefore the force is then, directly proportional to Q1, Q2, Q1, Q2 divided by R square. Looks very similar to gravitational law, where the gravitational force was proportional to the product of the masses and inversely proportional to the square of the distance between them. Very similar, very similar. Yeah. So he converted that. Now, basically, you can convert that proportionality into equality. That constant of proportionality, we can call it as Coulomb constant. Rest of the things are as it is. This is Q1, this is Q2, this whole thing divided by R square. What is this K? This particular K is called as the Coulomb constant. Coulomb constant. Coulomb constant, which is basically K. It is also written down as 1 by 4 pi epsilon naught. The value of K is 9 into 10 to the power 9. The SI unit of K will be nothing but Newton. This is Newton. Meter and meter will go on the top, meter square. This is Coulomb and Coulomb. So divided by Coulomb square. That is the unit of it. What is this number and why it comes, you will understand in Gauss law. For now, just remember it is 1 by 4 pi epsilon naught. 4 is a constant, pi is a constant, epsilon is also a constant. Okay, you can see epsilon is also constant, and that is called as permittivity of vacuum or free space. Permittivity of vacuum or free space, you can easily find that value. It is not that big a deal. I mean, just see, K value is 9 into 10 to the power 9. This is 1 divided by 4 multiplied by 3.14 multiplied by epsilon naught. So therefore, epsilon naught will be 1 divided by 9 into 10 to the power 9 multiplied by 4 multiplied by 3.14. So solving this, you will get the value of permittivity. You will get the value of permittivity as 8.85 into 10 to the power minus 12. 8.85 into 10 to the power minus 12. That is the value of permittivity of free space or vacuum, basically. So all these things definitely you should remember. You should remember, including this. So the force of attraction or repulsion is K Q1 Q2 by R square. K is Coulomb's constant having a value of 9 10 to the power 9, which is also 1 by 4 pi epsilon naught being the permittivity, having a value 8.85 10 to the power minus 12. This permittivity is basically a factor which decides, is the number which decides how much is the electric force being permitted inside the medium. Later on, you will see, if you change the medium, the force of attraction and repulsion also changes. So for now, we will only deal with vacuum. Let's not change the medium around them. So that permittivity number is this 8.85. If you change it into gas, some medium, water, glass, etc., it will be completely different. Okay. So I hope, Kauchi, this is absolutely clear. Yeah. So permittivity is just a number which tells how much electric force is permitted inside that particular medium. So permittivity, that's what it means. Okay. So the permittivity of different medium is different. For now, we'll only deal with vacuum or air, almost the same permittivity. Okay, we'll not break our head on other mediums. That will come later on in this chapter. Okay, which is called dielectric medium. Yeah. Oh, all right. Um, Ambi Suresh, only lecture videos can help in JEE main preparation. Preparation for understanding theory, 100%. You have to watch video lectures or attend a live class or attend a actual physical class. Without that, you cannot prepare for JEE. But the true preparation happens much beyond that classroom or that teaching where you sit and solve problems. Okay. So watch the lectures. Just reading books will not be enough. You have to watch the lectures. You have to read the books. You have to solve a lot of problems and PYQs. Okay. Clear. All right. All right. All right. Now, now, till this point, you have understood. So let us just see some questions based out of it. Maybe we have uh, this question: charges on the spheres are this and this. If each of them is given an additional charge of this, just to, okay, before we go ahead, just a small thing. Say, for example, we take two electrons, okay? And if I ask you what is the force between them, two electrons are there. If I ask you what is the force between them, and let's say the separation between them is, there are two electrons and they're at a very small distance. Let's say, maybe 1 millimeter, example, 1 millimeter. 1 millimeter is this small distance. So let's try to figure out how much force is there between them. So the force value will be K Q1 Q2 divided by R square. What is the value of K? Standard 9 into 10 to the power 9. What is charge 1? It is the electron charge, which is 1.6 10 to the power minus 19. I am only interested in the magnitude of the force. I'm not interested in the exact positive, negative. That is not relevant for me. So just substitute the magnitudes only. Into 1.6 into 10 to the power minus 19. The whole thing divided by R square. Okay, so R square means 1 millimeter, which is 1 into 10 to the power minus 3 meters. And this is basically whole square. Is this absolutely clear? Okay, so what will this become? This will become 9 into 16 16s are 256. So this will become 2.56 multiplied by 9 minus 19. This will become minus 10. Minus 10 and minus 19 will make it 10 to the power minus 20. Whole thing divided by this is 10 to the power minus 6, right? Minus 3 and 2. So how much will this approximately be? 9 into 2.56. Come on, guys. 9 into 2.56. How much will it be approximately? Come on, guys. 9 into 2.56. 9 2s are 18. 9 3s are 27. So somewhere in between of that, like 22 or 23 or 24, like that. Yeah. And what is the power of 10 that you will get? You will get the power of 10 as minus 14. Yeah. How much is it coming out to be, guys? 25. Ninja. Come on, guys. 223. Yes, 23.04. Okay, says Ibu. Yes, sir, Rathai, I'm giving full content only. Yeah, very good, very good. 23.04 into 10 to the power minus 4 Newton. What does this tell you? This force is very, very small. I mean, usually you have hundreds or tens of newtons. This is so, so small. So then you might even think that, sir, is it even worth it doing this chapter when these forces are so small, and that too 1 millimeter is a decently small distance? Then you might start thinking, sir, I think the distance is very large. Let's reduce the distance. Okay, even if you reduce the distance, maybe it will go from minus 14 to minus 8, minus 9. But still it is very small. So then it might feel like, yeah, yeah. Then it might feel like, did we miss on something? Oh, okay. Sorry. We made a mistake over here. Power of 10. My bad. This was 9 and minus 19, which is minus 10. Minus 10 and minus 19 is minus 29. and this was 10 to the power minus 6. Is that right? So this will become basically minus 23. Is that fine now? 10 to the power minus 23. Just check it out. Yes, Akansha. Perfect. Yep. Now, Cauchy, never use the sign of the formula in the, sign of the charge in force formula, because you already show the direction. You use the sign only in the formula of potential energy. Okay, because their potential energy is scalar, but the positive negative value matters. So only in the energy scenarios use the sign, but otherwise for forces and fields, don't have to worry about the sign of the charge in the formula. But while showing the arrow mark, if you show it correctly, whether it is repelling or attracting, your job is done. Your job is done. Okay, perfect. The answer to this question is, if you just try to find the acceleration, the acceleration, just check this out. Acceleration is force by mass. So it will be 23.04 into 10 to the power minus 23. And the whole thing divided by mass of an electron is 9, okay, into 10 to the power minus 31 kg. That's the mass. It's very small. Oh, by the way, we had already multiplied by 9. So if I divide by 9, I will just get roughly around again 2.5. Yeah, 2.56 into 10 to the power. What am I going to get? This is minus 23. This is minus 31. 31 goes on the top. So 31 minus 23, that is basically 8 meters per second square. This is very, very large. That is why we should consider this. Although the force is very small, but the acceleration is like crazy. The acceleration is crazy. That is why we consider these electric forces. Is this clear? Yep. Perfect. Perfect. Q E by M, Rathal, that is the wrong formula. That is Q capital E by M. E is electric field. You are getting confused. Yeah. So don't get confused. So go with the flow, Rathal. You're just doing step by step. We have not even discussed electric fields. We have just discussed electric forces. Okay. So now let's do this particular question. Let's see if you guys can figure this out. Charges on two spheres are so and so, and they experience a force of F. If each of them is given an additional positive 2 charge, then what is the new force between them? Okay, let's understand. This is plus 10 microcoulomb. Some R is there. This other one is minus 5 microcoulomb. So obviously there will be a force of attraction between them. And that force magnitude wise will be Coulomb constant into 10 into 5. But there are 2 micros over here. We'll put 10 micro into 5 micro, whole thing divided by R square. This is what the force magnitude will be. Just don't substitute anything, but this is what it looks like initially. Now what have you done? Each one of them is given positive 2 charge. So what will happen to minus plus 10? Plus 10 will become plus 12 microcoulomb. But the distance is still the same. What will happen to minus 5? Minus 5 plus 2 will become minus 3 microcoulomb, not minus 7. Lot of people make mistakes. Azad, what is the unit of acceleration? Isn't it meters per second square? This is Newton, right? And this is kg. So what is Newton by kg? Meters per second square? Yeah. And it is acceleration, right? What is this that we found? Acceleration. What is the unit of acceleration? Forgot. Okay, no issues. Happens. Still, there will be attraction only between them. Let's say the new force is F1. New force is F1. What will that F1 be? Coulomb constant. Charge 1 multiplied by charge 2, which is 3 micro. Whole thing divided by R square. I feel the best thing to do will be divide both of them. Yeah, just divide both of them. Just take F1 on the top and just take F below and see what exactly do you get. The moment you divide both of them, a lot of things are going to get cancelled, guys. See, like you have K into 12 micro into 3 micro, whole thing divided by R square, and same thing over here also. K divided multiplied by 10 micro multiplied by 5 micro divided by R square. A lot of things are going to get cancelled, like this R square, micro with this micro and this micro, this K and this K will also get cancelled. I think we can also cancel maybe 12 with 2 times will become 6, 10 with 2 times will become 5. So I think we are just now left with what? 6 multiplied by 3, and this is nothing but 5 5s are 25. So 6 3s are 18 by 25. So therefore, what is the value of F1 that we'll get? F will go on the top, and this will be nothing but 18 by 25. So 18 by 25, F, which is C option, is the right answer. So we had to use Coulomb's law 2 times and we got the right answer. Isn't it marvelous? Loved it? Everyone? Yeah, perfecto. So this is how Coulomb's law based questions can come in your JEE examination. Let us see another question which came in JEE 2022 PYQ. Let's solve direct question on Coulomb's law. Two identical metallic spheres A and B are placed at certain distance and they repel with a force of F. Another uncharged sphere is first placed in contact with A, so conduction, and then in contact with B, another conduction, and then finally placed at the midpoint of the two spheres. The force experienced by sphere C will be. Okay, let's try to get this right. So we have this guy, over here. So there are three spheres. This is A, this is B, and let's say this is C. A are placed at certain distance. Okay, and two identical metallic spheres A and B are placed at a certain distance in air and they repel each other with the force of F. Another identical uncharged sphere is C. Okay, this has zero charge right now. Is first placed in contact with A. Okay, so let's assume this guy has some capital Q charge. So if you touch C with A, what will happen? This charge will get divided. So won't this become Q by 2? And on this guy, you will get basically Q by 2, guys. Everybody, the moment you touch sphere C with connected with A, this charge Q will get divided like this. Okay. What about this B sphere? It had some charge Q, which I don't know what it is. I'm just putting it as small q. Okay. Now, identical metallic spheres A and B when placed at a certain distance. Okay, the spheres are also identical. That means the charge will also be identical. Okay, so this is also, let's say, Q. So this is also going to be Q only. They are identical metallic spheres. Okay. Now, what you are doing, first the sphere C touches A, then that same sphere C touches B. Same sphere C touches B. Okay. So when you touch B, what will happen to B? A will not change, Q by 2 will still remain. These two will exchange the charges. Just imagine how much was the total charge on both of them. It will be Q plus Q by 2, which is 3Q by 2. Now this 3Q by 2 will get divided equally. How will it get divided equally? 3Q by 4 and 3Q by 4. So hence on this guy the charge will be 3Q by 4, and on this guy the charge will be also 3Q by 4. Is this now absolutely clear? Why 3Q by 4 and 3Q by 4? Yes, the total charge conservation, remember. Both of them are touched, the total charge will be 3Q by 2. When you separate them, both have to get, equilibrium, and they have to finally get equal distributions of charge because they are all identical in nature. So 3Q by 4 and 3Q by 4, everyone, till this point, absolutely clear. Now, what is done? In contact with A and finally placed at the midpoint between the spheres A and B. So you take this sphere, it is placed at the midpoint of A and B. That means over here like this. This is q by 2 and this is basically how much? 3q by 4. 3q by 4. You are placing it at the midpoint. Earlier, if I just duplicate this, earlier, when only A and B was there, where only A and B were there and they were nicely repelling each other. They were nicely repelling each other. Let's say the distance between them was, say, x. Okay. So that force was q divided by x square. So it is q square by x square originally between A and B. Originally between A and B, that was the force. But now the question is, now what is the force experienced by this sphere C when it is at the midpoint? First of all, do you realize this will be x by 2? This will be also x by 2. This with this will repel it this way. It will repel it like this. And this sphere with this sphere will repel it in this direction. Are you able to visualize this? This charge q by 2 will repel this charge, positive charge, this way. This charge will repel this charge like this. Both the forces will act together. Both the forces will act together. Okay. If it is asking to fill the, just check your profile dashboard. I'm pretty sure you will see that Vikas Ganesh. Okay. Now, what is this value of the force? It will be K charge 1, charge 2. That means 3q by 4 into 3q by 4. Whole thing divided by x by 2 whole square. How much will it come out to be? Just carefully analyze that situation. 3 3s are 9. So k and q square. Whole thing divided by 4 4s are 16. X square is there here. 2 square is 4 but goes on the top. 4 cancels with 16 and you are left with 9 by 4 kq square by x square. 9 by 4 kq square by x square. Everybody clear till this point? Okay, 3 3s are 9, 4 4s are 16. X square, 2 square is 4 but 4 is going to go on the top numerator. 4 and 16 cancel, so 9 by 4. Similarly, we can calculate this guy also. So it will be k into q by 2 into 3q by 4 whole thing divided by x by 2 the whole square. So what will this be equal to? So 3 will be there in the top, k will be there, q square will be there, whole thing divided by 4 2s are 8. This x square will be there, 2 square will be 4, it will go on the top. So 4 and 8 cancel, so it will become 3 by 2 k q square by x square. Now tell me, among 3 by 2 and 9 by 4, who is bigger? This is 1 by 5, this is 2.25. So this yellow one, this is more, this is less. So what will be the net force on it? So think about it. What will be the net force on it? What will be the net force on it, guys? Yes, what will be the net force on it? That new force or that net force on it will be this minus this. So it will be 9kq square by 4x square minus, because it is opposite, so minus 3kq square divided by 2x square divided by 2x square. Is this absolutely clear? Perfect. So what will happen in the next case? Check this out. Kq square by x square is common. 9 by 4 minus 3 by 2. Let's just play with the brackets. Take the common LCM, which is 4. So that will be 9 minus 6. So 9 minus 6 is basically 3. So you will get 3 by 4 over here. But what is kq square by x square? What is kq square by x square? It is right over here. It is basically your f. It is basically your f. Can you see that? Yep. Perfecto. Yes. Can you see that, guys? It is nothing but this kq square by x square is nothing but your f. So why not replace that with F? Why not replace that with F? So it is nothing but 3F by 4, which is option B. Option B is the answer. This was a JEE mains question, so it is very lengthy. It is not difficult, it is very lengthy. Chances of making silly mistakes are huge. First part, okay, both charges are there, the force is this much. Next, you are connecting this charge with this. So, the charge got this charge with this. So the charge got distributed. Then these two are connected to each other. So their charge got distributed. Then you take this charge and place it in between. So this guy will repel. This guy will also repel. So the forces you calculate separately. Then you see how much is the net force because they are opposite. And then you realize, oh, wait a minute, kq square by x square is actually that original force, F. So you replace it and you get it as 3F by 4. So very lengthy question in JEE mains can also come like this. I hope you guys got it. Yeah. So these kind of questions can also come in the examination. Now, what we did actually was we skipped one theory concept deliberately because I wanted to see whether you guys understand this question. And that was actually force between multiple charges. Tarun, you will get the PDF after the lecture is over by tomorrow. In the description box as well as in the comment section, we upload it on our servers so that you can download it. Okay? Don't worry. We actually did something called as the principle of superposition. Principle of superpositioning. What is this principle of superpositioning? It says that if you have multiple charges, each charge will apply the force onto you, and the net force will be just the vector addition of all these forces. So it's as simple as the net force on a charge, the net force on a charge is the vector sum of all electric forces, due to other charges on it. So say for example, there is a charge over here, capital Q, and there is a charge over here, let's say Q1, then Q2, and let's say Q3 and Qn, and so on and so forth. First of all, this charge with this with this, and so many others will have some distances. It could be R1, R2, etc. Maybe maybe this charge is attracting, maybe they are opposite, maybe this charge are repelling, maybe this charge is attracting or repelling, who knows. So like that, all these forces will be there, F1, F2, F3, etc. So maybe this is F1, maybe this is F2, maybe this is Fn, so on and so forth. So the net force on Q, the net force on Q will be force due to the first charge, second charge, like that, till force due to the nth charge. That is exactly what superposition principle is when you have multiple charges. When you have more than one charges around you, then every charge will apply its own force. This will pull, this will push, this will pull, this will push. The net force will be the vector sum of all these forces. That is exactly what we did. That is exactly what we did here. This charge pushed, this charge also pushed. The net force was right over here. The net force was right over here. The vector sum of both of them. Because they were opposite, so we had to subtract their magnitudes. Is that clear? Isn't it? Actually superposition principle, my dear students. Isn't it actually superposition principle? Yeah. Very good. So let's see a question based on superpositioning. There could be multiple questions on superpositioning, like say for example, you have a triangle like this, and let's say you have a positive charge over here, you have positive Q over here, you have positive, you have positive Q over here, And let's say over here, you have another positive capital Q. And let's say I tell you this is A, and this is also A. And now I tell you what is the net force on capital Q. What is the net force on capital Q? This is the question. How will you do this, guys? Come on, think and tell me. How will you find the net force on capital Q? Simple superpositioning principle. So think which are the charges which will apply forces on capital Q. One is this guy. This guy on this guy will push it because it is repulsive, of same charges, same sign, like this. Let's say I call that as F1. This positive will also repel, and it will be probably like this. Let's say I call it as F2. How much is F1 and how much is F2? Not very difficult to find. F1 will be, the charges are K, Q and Q separated by a distance of A, so A square. How much is F2? Coincidentally, charges are same, distance is same, so K, Q, Q divided by again A square. Good thing both are same. Now, these two forces together will produce a resultant somewhere like this, isn't it? This would be the net force on it. But how do I find the net? Guys, vector addition. Do you see these are two vectors making certain angle between them? Can you see there is some angle which is made between them? How much is that angle? Not that difficult to figure out because this is 60 degrees. This is equilateral triangle. So obviously, even this is going to be 60 degrees. Oh, perfect. So how do I find the net force? The net force will be nothing but root of f1 square plus f2 square plus 2f1 f2 cos theta. This is the vector addition formula you have learned in 11th standard, one of the first few chapters. Oh, so all I need to do is substitute the value of f1 and f2. But wait a minute, these values are so big. So I have an idea. Why not just assume it as x? Let me just assume it as x. I will substitute x later on. It will be convenient for me. So f1 is nothing but x square. f2 is also x square. f1 x and f2 is also x. I've just substituted f1 and f2 as x. That's all. Cos theta will be nothing but cos of 60 degrees. Cos of 60 degrees. Okay, x square is common everywhere. So what I will get is, just observe this. This is x square common. 1 plus 1 plus 2 multiplied by cos 60 is nothing but half. X square's root is just x, and you are just left with 1 plus 1 plus 1, which is nothing but root 3. But I know the value of x. X is basically this. So it will be k q q divided by a square root 3. That is your net force. Use vector addition to solve the questions. Use vector addition to solve the questions. Yes, that is your net force. You can also get questions like this. You can also get questions like this, where instead of a triangle, you might have a square like this. This is also one of the most common questions. This is A, this is A. Maybe Chuma, I'm taking something. This is Q. This is, let's say, minus Q. This is, let's say, Q again. And let's say this is minus Q. Can you find the force on the positive charge? Can you find the force on positive Q due to other charges? This is also one standard question. Okay, you can have other charges also, nothing like that. So again, do the same logic, guys. I mean, see, this is positive, this is negative, so that's why they will attract each other. And that attractive force will be nothing but K into Q divided by A square. All right, or if you want, I'll just call it as F1 over here for now. That magnitude of that force will be K Q divided by A square, which is just KQ square by A square. Similarly, even this negative and this positive will attract each other. And obviously, we can find out that magnitude, which will also be the same only kqq by a square. Magnitudes are same, distances are also going to be the same. Now, imagine this charge and this charge, they are both positive. What will happen? They will repel each other. Let's say I call that particular force as F3. Just be careful of one thing though. The distance is not A, rather it is the diagonal distance. And how much is basically the diagonal? The diagonal, you can use Pythagoras theorem over here. This is nothing but root of a square plus a square, which is nothing but root 2 times of a. That is the distance between these two charges. So technically speaking, that F3 will be K into Q divided by root 2 times of a whole square. So it will be K Q square by 2a square. These are the forces. These are the forces. But that is not the job. I have to find the net force. I have to find the net force. So forget all these things for now, for a moment. Just forget this now. Just concentrate only on the forces now. F1, F2 and F3. Rest everything else you forget. I feel the first thing you should do is solve F1 and F2 because their resultant will be over here. So F1 and F2 resultant will be like this. So if this is F1 and let's say this is F2, this is F2, this is F1, this is the resultant of F1 and 2. I will call it F1, 2. How much will F1, 2 be? One good thing is F1 and F2 are both of the same magnitudes. So even if I do root of F1 square plus F2 square, I just know one thing, that since they are same in magnitude, I can just do this. So it will be nothing but root 2 times of F1 or root 2 times of F2. One and the same thing, because F1 and F2 coincidentally are the same. Oh, so that is F1, 2. So I don't have to worry about F1 and F2 anymore. So just think now, you have one force which is like this, which is F12, and the other force which is remaining is just that F3 force, is just that F3 force. Oh, both these forces are opposite, but they are not equal. As you can see, kq square by 2a square. This is nothing but root 2 times of F1, which is as good as saying this is root 2 times of F1 or F2, which is kq square by a square. So they are opposite of each other. Which one will be more? Obviously, F12 is more as compared to F3 because F3 has 2 in the denominator. F12 has root 2 in the numerator. So this is higher. So this is bigger, this is smaller. So there will be a resultant force like this. This would be the net force. This would be the net force, and that net force will be the subtraction of this F12 with this F3. With this F3. F12 is bigger as compared to F3 because of these values that you can see directly. Just compare them. You are seeing this is more than this. So just have to substitute. F3 is nothing but kq square by 2a square, and F12 is nothing but root 2 times kq square by a square. That's it. So solve this, guys. You are going to get the net force. So kq square by a square is common. You will have root 2 minus 1 by 2, which you can also write it as kq square by a square, 2 root 2 minus 1, and this 2 will be there downstairs. That's all. That is the final answer. That is your net force acting on that particular charge. Net force acting on that particular charge. Is this absolutely clear how to solve this kind of question? Okay, so you can get these kind of questions of triangle, or I don't know, even square or hexagon. It's all vector addition at the end of the day. So the first thing in that square problem, what we did was we identified which charges are applying the forces, like this guy pulled, this guy pulled, this guy repelled. We never substitute the signs in the equations because I've already shown the direction. So don't put negative signs. Okay. And once I got that, I realized that these two forces are perpendicular. Let me solve it and find their resultant. And that resultant I added with the remaining force F3 over here, and I got the net force, which is unbalanced, okay, or remaining. That's how you solve this, guys. So I think I have kept a question for all of you as homework. Yeah, I want you to solve this. Substitute everything, whatever you know. Give the answer in the comment section. Next lecture, I will be opening the comments of this lecture and seeing how many of you solved it, and as soon as possible. Even if you're watching it recorded, don't worry. Don't think that, oh sir, I will be solving it late, this, that. It's okay. Just solve it and give me the answer in the chat box. Yes, the solution, the answer will also be given to you in the PDF of this particular lecture, which you can download later on. And I hope that you're not going to see the answer in the PDF. Okay. So without seeing, try to put up the answer in the comment section. I want everybody to make this a habit, whether it is simple question, laddu question, difficult question. Get into that habit of consistently solving questions. Okay. So do this, put up the answer in the comment section. All right. So that's it for today. That was lecture 1 of chapter 1 of 12th standard physics. Lecture 2 will be now on fields, and so on and so forth. We'll go to slowly, potential energy, then dipole and dielectrics, and that's how we complete the chapter. And then Gauss's law is also there, applications of Gauss law is there. So many things are there. But we have divided the classes into small bits. Okay. So be there for every single class. This is one of the most important topics of 12th standard, and that decides whether you'll understand capacitors and then current, electricity, and so many other things throughout the physics syllabus. Okay. So thank you so much for liking. If you're not yet subscribed, please subscribe, and God bless you all. Take care. Good night.